Welcome to the course on an introduction to information theory. Now, in this lecture, we are going to talk about Shannon's noisy channel coding theorem. We are going to prove the achievability part of the result, and we are also going to prove the converse of this theorem. In the last lecture, we have already built up the background to prove our noisy channel coding theorem. So, we start our lecture with some basic definition and model of the communication channel that we will consider. So, W is our message that we want to send. It's encoded using this encoder, and X of n is our code word that is transmitted over a discrete memoryless channel whose transition probability, channel transition probabilities are given by probability of y given x. Yn are the received noisy code words, and the job of the decoder is to estimate what was the message signal that was transmitted given received sequence Yn. Now, an error happens if W is not same as W hat, otherwise there is no error. So, this is the communication channel model that we are considering. I'll first define few terms before I go into the noisy channel coding theorem. So, we define a code by these parameters m and n. I'll explain these terms in a little while. And a discrete memoryless channel is described by this input x, output y, and channel transition probabilities which are given by probability of y given x. So, this index set will be basically used to denote will be correspond to each of these messages, and what we are going to do, our encoder is a mapping of this index set to an n bit sequence, and this we are denoting by x of n. So, we will have n code words. This is xn1, xn2 denoted by xn3, xnm. So, these are our set of code words, and we will refer to our set of code words as code book. Now, as you saw, once you send these xn's at the channel output, at the receiver input to the receiver, you will receive y of n. So, once you receive y of n, then you essentially need to find out which of these m messages were transmitted. So, decoding is essentially the inverse operation. So, it is a deterministic rule that assigns a guess to each possible receipt vector. N is the length of the code word, and m are number of code words that we have. Lambda I is nothing but conditional probability of error given that index I was sent. So, I sent index I, what is the probability of error? Now, when will an error happen? If the decoded, so decoder function is denoted by g. So, if g of y of n is not same as I, and when you transmit ith index. So, when x of n is x of n I, when you transmit the ith index, but your decoder does not decode it as ith index, then the error happens, and that is given by this, where this is an indicator function indicating whether error has happened or not, and this is a probability of yn given x of n I. So, this is, so lambda I is the conditional probability of error given that you transmitted the ith index. Now, we define maximal probability of error as maximum of lambda I over all possible indexes. So index I can go from 1 to m. So the maximum of lambda I, that's the maximal probability of error. Similarly, we can define average probability of error. So lambda is the error when ith index is n. So when you sum over all lambda i's and divide by m, you get average probability of error. It's not very difficult to show that this average probability of error will be less than this maximal probability of error. Now we are going to show you later in this lecture that as long as our transmission rate is below channel capacity, our average probability of error is very small. It goes to 0 as block length, code word length increases, and we will show if the average probability error goes to 0, then the maximal probability of error also goes to 0 as n becomes large. So as I said, the total m indexes that we are sending, so the number of information bits are log of m and the code word length is n. So the rate of the code is denoted by log of m divided by n. Now we say a rate is achievable if there exists a sequence of codes with parameter m given by ceil of 2 raised power nr and of length n, such that the maximal probability of error goes to 0 as n goes to infinity. So we say a rate is achievable if for that particular code with parameter 2 raised power nr n, the maximal probability of error goes to 0 as the code word length increases. And we define the capacity of a discrete memoryless channel as the supremum of all achievable rate. So supremum is the smallest, basically upper bound of a set. So capacity is basically supremum of all achievable rates. Now for a discrete memoryless channel, Shannon's noisy channel coding theorem says that all rates below channel capacity are achievable. That means if we transmit at a rate below capacity, then our maximal probability of error will go to 0 as the code word length increases to infinity. So specifically for every rate which is less than capacity, there exists a code of these parameters such that maximal error probability goes to 0. Now we are going to prove the achievability part of this theorem first. So first we are going to show that average probability of error goes to 0 as n becomes large, and then we will show that if the average probability of error goes to 0, then the maximal probability of error is also bounded and it also goes to 0. So first we do is we fix our input distribution and generate 2 NR code words according to this distribution, ID distribution, and we consider a row of matrix where each row is basically randomly generated code words. So this x1n, x2n, xn is code word. Similarly these, so we generate 2 raised to power 2 NR code words and they are stacked up in a matrix like this. This is randomly generated. So probability that we generate a particular code C is given by this probability. So probability of xiw, where this w can go from 1 to 2 raised to power nr and I goes from 1 to n. Now once we randomly generate a code, we reveal this code to both the sender and the receiver. Now we assume the channel transition matrix probabilities are both known to the sender and receiver, and we choose a message W according to uniform distribution. So, probability that we choose a particular index is given by 1 by 2 to the power 2 NR. So, that is this probability. Okay. And the Wth code word corresponds to the Wth row of this code matrix that we talked about. So, when we select this index W, we are actually sending this Wth row of this code word matrix that we talked about, that we are randomly generating. Now, what the receiver receives is y of n, and probability of y of n given a particular xn of W was sent. This probability for a discrete memoryless channel without feedback is given by this expression. Now, once we receive yn at the receiver, we are going to do what we call jointly typical decoding. So, we are going to do a typical set decoding. Now, this is a suboptimal decoding technique, but asymptotically this is basically optimal. So, how does a typical set decoding works? It works as follows. So, the receiver declares that an index W tilde was sent if the following conditions are met. And what are those following conditions? If x and W tilde and yn, which is the received sequence, if this is jointly typical and there is no other index k such that xn k and received sequence y of n are jointly typical. So, we say that we successfully decode an index if xn wn, that index, and y of n, they are jointly typical and there is no other index for which xn k and yn are jointly typical, and that is basically your typical set decoding. So, when will an error happen? An error will happen when you send W index and you decide in favor of some other index which is not W. So, an error can happen in a typical set decoding if there is no W tilde. That means there does not exist any index for which this pair, the xn W tilde y, it is jointly typical. That is one condition. Or the second condition under which an error can happen is as follows. If there is more than one such index for which xn k and yn is jointly typical. So, there are two possible cases of error. One, if there does not exist any index W tilde such that xn W tilde and yn are jointly typical, that is one condition. Second condition is there exists more than one index for which xn k and y of n are jointly typical. Then also we will make an error, decoding error. So, let us try to calculate what is the average probability of error, and we are calculating this average probability of error, average over all possible code words and averaged over all possible code books. So, this is a probability of error for a particular code book, and this is a probability of this code word C. We average it out over all possible code books. So, this probability of error from definition, this is given by this, as you recall, is 1 by m summation W1 to m lambda WC, right. So, this can be written like this. Now, please note that this term does not depend on the index W. Why? Because the way we are constructing our code, due to symmetry of the code construction, the average probability of error average over all possible codes is not a function of a particular index. Now what does that mean? It means that then we can calculate our probability of error given a particular index has been sent. Since it does not depend on what index, probability of error does not depend on what index have been sent, so we can calculate our probability of error assuming a particular index I was sent, and that is what we are going to do. So without loss of generality, we will assume that, let us say, the first index was sent, and we are going to calculate probability of error given the first index was sent. So the probability of error can be given by probability of error given the first index was sent, and that is probability of error given index 1 was sent. So let us compute this probability. Now let us denote EI to be the event that ith code word and receive sequence Y of n are jointly typical. So EI is the event that xni and yn belongs to jointly typical set. Okay. Now as I said, probability of error does not depend on what index has been transmitted. So we will do an analysis assuming, let us say, index 1 was sent. So what is the probability of error when index 1 was sent? So this is given by, so as I said, this is given by probability that, what is E1C? E1C corresponds, now if index 1 was sent, the decoder will not make an error if xn1 and y of n are jointly typical, and that corresponds to event E1. So if E1 complement happens, then that is an error, because if index 1 has been sent, the decoder will not make a mistake if event E1 occurs. So an error will happen if the complement of event E1 has happened, or error can happen if any of the other index which was not sent is jointly typical with the received sequence Y of n. So for example, if yn is jointly typical with xn2 or xn3, then there is an error because index 1 was sent. So union, so I can write upper bound probability by, I can write it as probability of E1 complement union of E2 event, union of E3 event, union of up to E of 2n are given that first index was sent. Okay, and using union bound, I can upper bound it then as probability of E1 C complement given index 1 was transmitted plus probability of EI given W index 1 was transmitted and I goes from 2 to 2n r. Okay. So this corresponds to the event that yn is not jointly typical with, if you go back and see, this corresponds to event, E1 corresponds to the event that xn1 and yn are jointly typical. So this corresponds to the event that xn1 and yn are not jointly typical, and this corresponds to the event that any other index, let us say xn2, xn3, xn4, they are jointly typical with y of n. Now, so then the error probability is upper bounded by this probability and this probability. Now from the property of joint AEP, we know that if n is very large, then x of n1 and y of n are likely to be jointly typical. We have shown property of jointly typical sequence, that probability that x of n1 and y of n belongs to a typical jointly typical set, that probability goes to 1 as n goes to infinity. So then this probability that event E1 complement happens given that W is 1, this probability is going to be very small, it is less than epsilon. Now let us look at this. Now we have also shown that if xn1 and xni, where I is different from 1, they are independent, so yn and xni are also independent, then probability that yn and xni are jointly typical, this probability is upper bounded by 2 raised to the power minus n times mutual information minus 3 epsilon. This also follows from the property of joint typical sequence. This we have proved in the previous lecture. So when xni and y of n are independent, probability that they are jointly typical is upper bounded by this. So then we can compute the probability of error. As we said, it is independent of what index we have sent, that is because the symmetry of code construction. This is upper bounded, we have shown by probability of the complement of event E1 happening given index 1 was sent plus this probability. Now this from the property of joint AEP is a very small quantity, we are calling it epsilon. This we know is upper bounded by this probability. Okay. So when we sum it over from I equal to 2 to 2 raised to the power nr, what we get is this is equal to epsilon plus 2 raised to the power nr minus 1 times this quantity. Now we will just collect terms, we will collect terms containing epsilon. So this will become epsilon plus 2 raised to the power 3 n epsilon times 2 raised to the power minus n mutual information minus r. Now as long as our transmission rate r is less than this quantity mutual information, this particular term is going to be greater than 0, and for large n, so this term is greater than or equal to 0, and for large n 2 raised to the minus n, this term will go towards 0. So if n is sufficiently large and our rate is less than, see this you can combine as 2 raised to the power minus n minus 3 epsilon minus r. This is what you will get. So as long as r is less than this quantity, epsilon is very small, this term will be positive. For large n, this whole term will go towards 0. So some epsilon we are calling it. So this will be less than some small quantity epsilon. So what we have shown here is probability of error, that is probability of decoding, making a decoding error, is less than 2 times epsilon provided our transmission rate is below this mutual information between x and y minus 3 epsilon, and provided this length n is very large, as n goes to infinity. Now we can tighten this a little bit. So if we take r to be less than or equal to mutual information, and we can choose our epsilon and n such that probability of error is less than 2 times epsilon. Now we can now choose our P of x. Remember, we were generating our code words using this distribution P of x. Now we can choose our P of x such that we choose a distribution that will maximize mutual formation. So we can choose a distribution, I am calling it P star x, that will achieve capacity. Then this condition R is less than mutual formation can be replaced by the condition that R is less than capacity. Okay. So what I have shown you so far is average probability of error over all possible code words is very small. It is basically less than equal to 2 times epsilon. Now if the average error probability is small, that means there exists at least one code word whose probability of error will be less than the average probability of error, right? And remember, in the beginning we said that if average probability of error goes to 0, we can also show that maximal error probability will also go to 0. So that is what we are going to show now. Now what we have shown so far is the average probability of error, provided the transmission rate R is less than capacity, is less than equal to 2 times epsilon. Now what we do next is as follows. We throw away half of the code words. And what are these half of the code words? We throw away worst half code words. So we throw away code words which causes larger error. So we throw half of them. Now we are left with other half which consists of good code words, and by good I mean the ones which will cause less probability of error. Now it can be shown that for these half code words the maximal error probability is less than 4 epsilon. So for these best half code words the maximal error probability is less than 4 epsilon. The reason being, if it is more than 4 epsilon, then the average probability of error overall, bad and good code words, cannot be less than 2 times epsilon. So by throwing away half of the worst code words, we have shown with the half the number of code words left, we have shown that the maximal probability of error is now bounded by 4 times epsilon. Now since we have thrown away half of the code words, so we can re-index these code words, and now we have 2 raised to power nr divided by 2, that is 2 raised to power nr minus 1 code words. So now we have constructed a code with rate, I am calling rate r dash, which is r minus 1 by n, whose maximal probability of error is less than 4 times epsilon. So if n is very large, so there is hardly any rate loss, and you can see the maximal probability of error goes to 0 as n is large, because maximal error probability is bounded by upper bounded by 4 times epsilon. So this proves that when our rate r is less than capacity, then we can reliably communicate, because we have shown that the maximal probability of error is bounded by 4 epsilon. Next we are going to show the converse of this theorem. Now what is the converse of this theorem? So we are going to show that if our transmission rate is above channel capacity, that is our R is greater than C, then probability of error is bounded away from 0. So we will show that if transmission rate R is more than channel capacity, then probability of error is non-zero. So if information bits, so we consider a binary symmetric source, if information bits from binary symmetric source are sent at a rate R via discrete memoryless channel whose capacity is C, then probability of error is lower bounded by H inverse 1 minus C by R, where the transmission rate is above capacity. So if the transmission rate is above channel capacity, then probability of error is lower bounded by a quantity which is non-zero. And this h of p is nothing but our binary entropy function. If you recall, a binary entropy function looks like this, 0 to 1 at 0.5, this is 1. Okay. So to prove this result, let us look at the block diagram. So we have a binary symmetric source, the output of that are ui's, u1, u2, u3, uk, and these bits are fed to a channel encoder that generates these code words x1, x2, x3, xn. So the rate of the code is k by n. Now these code words are sent over a discrete memoryless channel. What you receive is yi, so you receive y1, y2, y3, yn. Now these are fed to a channel decoder which will try to estimate what were the information bits that were sent. So the channel decoder will try to estimate u1, u2, u3. So these estimates I am denoting by u1 hat, u2 hat, uk hat, and this is my sink. Okay. So let us now show that if the transmission rate is above channel capacity, then the probability of error is lower bounded by a non-zero quantity. So since we are considering a binary symmetric source, so probability of 0 and probability of 1 is half. It is a symmetric source and it is a binary source, so it emits zeros and ones with probability half. So we can write uncertainty in u as 1 bit. Now for a discrete memoryless channel without feedback, probability of y1, y2, y3, yn given x1, x2, x3, xn can be given by probability of yi given xi and product taken from I goes from 1 to n. So we can write the uncertainty in y1, y2, y3, yn given x1, x2, x3, xn by summation of uncertainty of yi given xi. And remember our transmission rate is k by n bits per use. So we are going to first apply data processing lemma. What does data processing lemma says? That further processing of data does not increase information. So what you had was we had u, x, y and u hat form a Markov chain. So mutual information between ui's and u hat i's, this is going to be less than mutual information between xi's and ui hats. So that is what I am writing here. Next, I again will apply data processing lemma. Let me write down the Markov chain. So u, x, y and u hat forms a Markov chain. So we have shown that mutual information between ui's and ui hat is less than mutual information between xi and ui hat. Now we can see that mutual information between xi and ui hat is less than mutual information between xi and yi. Again this follows from data processing lemma. So if we combine these two results, let's call it A and call it B. If I combine A and B, what I get is this condition, that mutual information between u1, u2, uk and u1 hat, u2 hat, uk hat, this is less than mutual information between x1, x2, xn and y1, y2, yn. Next, let us try to simplify this term, mutual information between x1, x2, x3, xn and y1, y2, y3, yn. Now from the definition of mutual information, I can write this as joint entropy of y1, y2, y3, yn minus conditional entropy of y1, y2, yn given x1, x2, x3, x of n. Now, since this is a discrete memoryless channel without feedback, this term can be written as summation of uncertainty in yi given xi. So, I can write this term as joint entropy minus the summation from I goes from 1 to n h of yi given xi. Now, this joint entropy can be written using chain rule as h of y1 plus h of y2 given y1 plus h of y3 given y1 y2 plus h of yn given y1 y2 yn minus 1. Now, this can be further written as this is upper bounded by h of y1 plus h of y2 plus h of y3 plus h of yn. Now, here I use the fact that conditioning cannot increase entropy. So, if I do that, then I can write that this joint entropy is upper bounded by summation of entropy of h yi where I goes from 1 to n. So, then from here I can write this expression as summation I goes from 1 to n h of yi minus h of yi given x of I. And what is this term? This term is mutual information between xi and yi. So, then I can write this as mutual information between xi and yi, and mutual information between x1, y1, x2, y2, that is less than channel capacity. So, I can write then mutual information between x1, x2, x3, xn and y1, y2, y3, yn, this is less than equal to n times c. Next, now we know that from data processing lemma, we know that this quantity is less than this quantity and this is less than n times c. So, mutual information between u1, u2, uk and u1 hat, u2 hat, uk hat, this will be less than equal to n times c. So, combining these results we get this. Next, let us define probability of bit error. So, basically this is sum of all errors divided by the block size, that will give me probability of bit error. And probability of error, when does an error happen? When my transmitted bit is not same as the decoded bit. Now, let us try to write uncertainty in u1, u2, u3, uk given u1 hat, u2 hat, uk hat. Now, this from the definition of mutual information can be written in this particular form. What is this quantity? The ui's are the output of a binary symmetric source, and this is independently identically distributed. So, h of u1, u2, u3, uk is h of u1 plus h of u2 plus h of uk, and h of ui was 1 bit because it is a binary symmetric source. So, this particular term will be equal to k minus this. Now, we have proved earlier that this mutual information is less than equal to n times c. So, if we subtract a larger quantity, this will become greater than equal to. So then this is greater than equal to k minus n times c. And what is k? K by n is r. So k is n times r. So when we write k as n times r and we take n out, what we get is uncertainty in u1, u2, uk given u1 hat, u2 hat, uk hat is greater than equal to n times r minus c. Now let us further simplify this term. So using chain rule, I can write this conditional entropy in this particular fashion, and as we know, conditioning cannot increase entropy. So this particular term can be upper bounded by uncertainty in ui given ui hat. So we have shown that this particular term is greater than equal to nc and earlier, and we are showing that this particular term is greater than this. Now combining these two results, we get that h of ui given ui hat sum over all i's from 1 to k, this is greater than equal to n times r minus c. Now what do we know from Fanno's lemma? From Fanno's lemma we know that uncertainty in ui given u hat is less than equal to Pe log of L minus 1, where this random variable ui can take L possible values, plus h of Pi. So this is, in this case, L is 2 because of binary random variable. So Fanno's lemma for this will be h of ui given ui hat is less than equal to h of Pi, because the other term Pi log of L minus 1 term, that's 0. So, and if we take summation over all I from 1 to k, both sides, we get this. So that's what I'm saying, using Fanno's lemma, we get this relation, right? And from what we proved earlier, we showed that this term is greater than equal to n times r minus c. So in other words, this particular term is lower bounded by n times r minus c. So we can write summation of HPI is lower bounded by n times r minus c, and if we divide both sides by 1 by k, so we divide both sides by 1 by k, what you get is on the right hand side n by k times r minus c, which is nothing but 1 minus capacity divided by the rate. Next, this binary entropy function is a concave function, and from Jensen's inequality, what do we know about the concave function? So Jensen's inequality says if the function f of x is concave, then expected value of the function is less than equal to function evaluated at expected value, if f of x is concave. So since this binary entropy function is concave, expected value of the function here is a binary entropy function, should be less than equal to function evaluated at expected value. And what is this term? This term is nothing but average bit error probability. Okay, so by combining this result with this result, we have shown that binary entropy function of this probability of error is lower bounded by 1 minus C by R, and remember R is greater than C here. So when R is greater than C, this is a non-zero quantity. So probability of error cannot be 0. So if we try to transmit at a rate above capacity, our probability of error will be non-zero. So this proves the converse of the noisy channel coding theorem. So with this, we will conclude our discussion on noisy channel coding theorem. Thank you.